Hi, this is a continuation for the last lecture about power commutation or waveform commutations. And today we are going to talk about the RMS values, and we will cover some examples. Last time we talked about how we compute the RMS value for a signal and what's the rule for this. And also today we are going to cover some examples and different waveforms just to make you confident with these examples. I will be showing some derivation for some of them and how we really got the final value, but I will leave for you some of them just to practice. Okay, so let's start now. So last time we have just stopped at this slide where we have the general RMS equation, and if we have two signals together composed, so we can really decompose them and also compute the average value for each one. So here's the first example. We have this signal here, and that signal we want the RMS value for it. Okay, so again the RMS value is the root mean square, so we can really start with the equation root mean square. Okay, so if we want to deal with this signal, okay, and to get the root and mean, I have to square it first. Okay, and what's the square of this signal? I think we have just I naught here, okay, and 0. If I want to square the 0, it will be 0. If I want to square the I naught, it will be I naught square, and it will look like this. Okay, so this signal now is I naught square, and this is what I want to get as average or mean, and then I will get the square root for this. So I have here again I naught square, and the I naught square now is from 0 to pi, and this is pi because now the duty or the period for this is t. Okay, and this is the, maybe we can say the on time for this. All right, what is I square t? I square t here, okay, has two values. The first value is I naught square from t 0 to pi, and it has 0 value from t pi to 2 pi. Okay, so the integration will be from 0 to pi because this what has a value. Okay, so now the integration will be just from 0 to pi for I naught square. Okay, and because I naught square is constant, so I can really take it outside, and it will be like this: I naught square divided by 2 pi, and the integration will be just for 1, and the integration for 1 is t. Okay, so now we have t, and after integrating it, it will be got the value from 0 to pi, and after recalculating the values, I will get the I naught multiplied by pi over 2 pi. Okay, look at the pi. The pi is here or here, the on time. Okay, and the 2 pi is the total period. So really I can say that's the square root of the on time divided by the full period. Okay, and I think most of you now know the duty cycle, which is the percentage of on time divided by the total period. So I can really say delta equals t on by t. We know delta, which is the duty cycle. So now the final answer will be like this: I naught multiplied by square root of delta. Now go for the average value. How we compute the average value? In the average value, we don't need to square it, okay, because the equation is just 1 divided by t square, integration from 0 to t I naught of t, or I of t. Okay, I of t here has a value of I naught from t 0 to pi, and value of 0 from pi to 2 pi. Okay, so the integration will be just for the period from 0 to pi for I naught. Okay, and because I naught is constant, so it will be outside, and the integration for just the value of 1, and that will be finally get to I naught equal pi over 2 pi, and again pi is the on time and 2 pi is the period, and really this will equal finally the I naught multiplied by delta, where delta is the t on divided by t. So I really can say if I have any signal that the on time has it's on the value of delta t and it has period of t, okay, like this. So the on time is not all the time by, it can be delta by, it can be quarter by, it can be any by, okay. So now it's portion of the total period, okay. So this is the duty cycle, really, the on time duty cycle, and this one is the total period. So I can get the general equation for the Rms value and average value, which is I naught delta for average value and I naught square root of delta for the Rms value. I can really get the average value by another way, because this equation is very easy. The average value is the area under the curve. And what was the curve that we have here? We have, this is our curve, okay? The area under this curve here, this piece here, is 0, okay? But the area here, from this to this, I think we know that the area is the area of this rectangle, which has the dimension of, this is pi, and this is I naught. So the area will be pi times I naught, okay? Plus the area of this one, which is 0. And all that will be divided by the total period, which is 2 pi, okay? So I can really get this, okay? And here is the other solution for this. I naught pi is the area for the rectangle, 0 is the area of the 0 period there, over 2 pi, and I will get the same answer, okay? Which equals I naught delta, okay? So if I want really to compute the signal for a pulsating signal like this one, which is very common, to be honest, and maybe this is one of the most important waveforms that we are going to use to calculate the power dissipation, because it's very popular and we really apply PWM. And the T on and Rms value will be like this, okay, because we already done it before. So the Rms value, it will be I naught divided by T on over T, and that's delta, and the average value is I naught delta. So if I have any other signal, okay, the period is T, and it has any on time, that on time is T on. And by the way, T on is also called delta T. It's the portion of T. That portion is the duty cycle, because what's the meaning of duty cycle? Is the on time, okay? So is the on time divided multiplied by T, it's the portion of that T is the on time, and that's the period. So the period, it will be a T, and the duty cycle, it will be T on, which is also can be written as delta T. I will tell you something. The T on equals delta T. That's for making the drawing easy. And the T off is the other portion, which is this time from there to there. What's that time? Is the T minus delta T. T, the full period, minus delta T, and will equal 1 minus delta T, okay? So delta T is the T on, or the first portion of the signal, and the second portion is 1 minus delta T, okay? Okay, let's memorize this and go to the second example, which is the DC value. If I have a DC value, it's not periodic, but we can really get the average value and the Rms value. And the peak for this is I naught. What is the Rms and the average? They are equal to I peak, okay? And just I will go for approval. Root of the mean of the squared signal, okay? What is that signal? My signal is I naught for all the periods, so it will be I naught. So I naught square is the squared signal. Now, because this is constant, so I can really take it out. So it will be I naught square divided by T, and that will be from 0 to T, 1 dt. And the integration for this one is T from 0 to T, okay? And this will be as it is. Again, this will be T minus 0, which is T, okay? I naught square divided by T. that t will go with that t, and it will be just I naught. And yes, we are right. Okay, for the average, it's just the integration from 0 to t I naught of t. You don't need to square it. And because this is constant, it will go outside, and the integration for 1, as we done here, the integration for 1, it will be cancelled with t, and the final value will be also I naught. Okay, so remember that DC value, RMS, and average value are the same, which equals the I naught itself, which is I peak as well. Another example, which is sinusoidal. I think you have done this before. The sinusoidal, the RMS value for sinusoidal is the peak value divided by square root of t. But the average value is 0. Why? Because the average value, now for the positive and negative portions, they are equal to each other and they cancel each other. Okay, so if you have a symmetric area between the positive and negative, so the average will be finally 0. And if you want to really approve this one, I will just start it. Okay, the RMS equals square root of the mean value, okay, from 0 to t. But for the squared signal, what is the signal is sine omega t, and actually it has a peak of I peak, so it should be here I peak, okay, sine omega t. Okay, after getting the square of that and follow the integration from the math, and maybe you don't need to memorize the integration of each signal or function, you can really use calculus or any other references to get the integration done, and finally you will get this value. Okay, so this is the RMS value and average value for a sine wave. But what about this one? This one is a result of sinusoidal wave gone through a diode, which is half wave rectifier. This one is a result of half wave rectifier. It passes the positive side and cancel the negative side, okay, or prevent the negative side. So what is the RMS value and average value for that? Because there is no symmetry between the positive and negative sides, so it has a new average value, which is I peak divided by pi, and the RMS value, it will be I peak multiplied by square root of delta, which is the duty cycle, divided by 2, okay, and here is delta t. That means if I have another signal which is a little bit wider or narrower, okay, so you can really calculate that without any pen. Okay, another signal which is the outcome of a full wave rectifier, which is this one. Okay, what do you think about the average first? The average, because we have here one area, but here we have two areas, okay, I think the average will be doubled, and really, yes, it's doubled here. Compared with this one, it's doubled. Okay, we have here 2 I peak divided by pi, but here I peak divided by pi. And for the RMS, it's exactly the same as the sinusoidal wave. Look at the sinusoidal wave. This one has also the same RMS value. So why the sinusoidal wave and the full wave rectification, okay, waveform, okay, they have the same RMS value? The answer is if you squared any signal and it looked like another signal, so the expectation is both of them will have the same RMS. So if I square this signal now, it will look like this. Okay, and if I square this signal, it will look like this. With some differentiation between, I just approximate the squaring, okay, but the sine wave and sine square, it's different a little bit, okay, but this is just approximation. So both of them, they are similar with the same also peak, so that's why they have the same RMS value. So the conclusion here, if you have two signals, they are different originally, but when you square them, they will be identical, so the RMS value will be also the same. Another example is this signal, which is bipolar signal. it has some portion positive and another one negative. So what do you think about the average? It will be 0 because asymmetric, okay? It has I peak value here, and the same I peak value in negative will be here as well. So the Rms value is I peak. Do you remember the DC value? It was also I peak, the Rms value for that. How the signal and the DC signal, they have the same Rms value? Because if you square this signal, it will look like this. This portion from here to here, it will has I peak square, okay? And this portion from here to here, when you square it, it will be like this. And continue. Okay, so it's the square of this signal is a DC signal, and when we go to the Rms value, it will be also the same as I peak, okay? But here the average value is different because we have now a different distribution of the positive and negative values. I think this is very simple now, but we have here I peak and the same I peak value here. We can really, the delta here, the delta t, or the t on and t off time are equal. So we assume that delta is half. Look at this one. Okay, this one has t on different from the t off. And here as well, the area of this portion is different from the area of this portion. What that means, the average is not 0 because the average will be 0 for identical positive and negative portions, but here is different. Okay, so that's why we can really see or expect average value not equal 0. What about the Rms value? What do you think about this one? If you square it, it will be also DC. So the Rms value is I peak again, and also the average value is different. All right. So we have here again, I mentioned before that the T on is delta T, and the T off is 1 minus delta T. Okay. So if I want to compute the average, for example, 1 over T from 0 to T, the signal itself dt, okay? And the signal is I peak from 0 to delta T, it's I peak, and from this point to that point is minus I peak. Okay, and that point to that point, actually it's the duration which is called T off, and that T off is 1 minus delta T. From 0 to 1 minus delta T, right? So here we have the average, and if you just do this, I will leave it to you, okay? You should finally come up with the value like that, all right? Now let's test the signal. If we do have a different negative value here, so it will look like this. So we have here different minus I peak and I peak, okay? Again, we have the on time is from 0 to delta T, and the off time from, for example, 0 to 1 minus delta T, okay? So you can really take these as the duration of time for integration, okay? So the Rms value is this equation, and the average value will be this equation. You can try it. There is no big challenge for this, and it's not really difficult, okay? But if you don't want to try it, no problem. At least you table them, okay? Because we are going to refer to that table every time we have this waveform, so we can really refer to that table and take the average value and Rms value. Okay, for this signal, I think we have seen it before, that we have turn on time for as delta T, and turn off time as 1 minus delta T, okay? And because we have here the value of this signal is during the on time, which is delta T, so now the equations are like this. But if I have a signal like this, the on time, or the waveform has a value during the 1 minus delta T, not during the delta T itself, okay? So what are the changes for this waveform, or for these values of RMS and average to be considered. And the changes is just to replace every delta with 1 minus delta. Okay, so that delta and that delta, which represents the where is the value of that waveform. Okay, it will be replaced by 1 minus delta here and 1 minus delta there. All right. So one of the things that, or one of manipulation that we can learn is, if we have a signal and that signal is just shifted to another period of time, I really can consider it by just changing the delta here. All right. So this is one of the things. Okay, what about this one? It's an AC signal, and from the beginning we have positive equals negative, so the average value will be 0. We have here I peak to peak, which is that value to that value, okay, which is delta I peak to peak, okay, and after deriving the average value, it will be 0. The Rms value, it will has this value, okay, which is delta I peak to peak, okay, or the ripple, we call it sometimes the ripple, divided by 2 square root over 3. Okay, so you can really memorize this one and leave it, because we are going to use this later. So I peak to peak divided by 2 square root over 3 is the triangular waveform. Let's look at this signal. What do you think about this one? I think this one is another triangular waveform, but it's shifted by a DC value up, or has offset. That means this signal can be decomposed to a DC value like that, okay, plus the triangle wave. I know the wave VRMS for this one, and I know the VRMS for this one, so I can really get the VRMS for the total one, which is the square root of VRMS square 1 plus VRMS for the second portion. This is 1 and this is 2. Okay, so by this way I think we can get the Rms value for the equation, all right, which is I naught square, okay, and that portion is from the DC portion, and that portion is from this portion. Okay, you can approve it by just applying this rule. And for the I average, we have it as I naught here. The average of the DC signal is I naught, and the average for this signal is 0. Okay, so it will be I naught. Okay, what about, look at this Rms value, please. Okay, we have this Rms value in terms of I naught, which is the average value here, and also I peak to peak, which is from that value to that value. Now the conclusion, if I just changed this waveform a little bit, but I maintained the average value I naught and maintained the ripple peak to peak similar, so I will get the same Rms. What I mean like this signal. If I have this portion now is shorter than this portion, that portion is longer than this portion. Okay, so I just shifted the maximum point here from this point to that point. That's it. So I just shifted that. So will that make Rms different? No, because it has the same I peak to peak, and also it has the same average value, and really I can get the same Rms value. And for the average value, because we didn't change the average values, it will be similar. What about this signal? This signal we can really go to the integration and compute it, but it will be a little bit challenging because we don't have here constant value like before. Okay, no, we have here linear signal, which is a line signal, and you have to get the line equation and integrate the line equation. The Rms value for that is I peak multiplied by a square root of delta over 3, and the average is I peak delta over 2. What about if I just changed the shape of this signal? I have this Rms in terms of I peak and delta. So if I just shifted this I peak to this place, keeping the same I delta, okay, so I have the same I maximum and the same delta t on time, so I think I will get the same Rms. okay? And for the I peak also, I will get the same, all right? Because if I kept the same area as well. So now let's have another example. If I have the signal as we just seen before, which has the this RMS value and this average value. But what about instead of making the signal on time on the delta t duration? No, I shifted that to 1 minus delta duration. So that duration from here to there is 1 minus delta t, okay? So what will happen to the average and RMS value? Instead of delta, I will replace it with the 1 minus delta, okay? So I want you to learn this because sometimes just you need to get the RMS value and you change it. If there are some parameters can be changed to something look like what you have in your question. Okay, what about this signal? I think again this signal is another two signals. One signal which is I naught plus another signal which is this one. It's a little bit different, okay, because the I naught is in the middle of this signal. So if I just subtract this, I will get this one, okay? After knowing the RMS value for this one and RMS value for this one, I think you can compute the RMS value and the average. And also if I changed here, because the peak to peak value, okay, I kept it the same, and the average value, I kept it the same, okay, for this signal. So the average, the peak to peak value are the same, and also the average value is the same, so I can get the same RMS value. And there is an important note here. This waveform in particular is very common as the signal passing through the diode, okay? And just to make it easy for us, to be honest, we assume it's like square wave, okay? Like this sometimes. And by assuming that, we are assuming really the rebel here and here is 0. Okay, so if I just make this 0 and make this 0, it will have just this portion there, which is the average and RMS value for a pulsating signal like this, okay? So they are very close to each other, but one has a rebel and one without rebel. And we usually, just for simplicity, usually we use this one for most of time. We will cover examples about this, but remember, this is the case, okay? So again, if I have signal like this, we computed the RMS value and average value, and we just repeated it more times, okay? So we have here, what do you think about the average value first? Because here we have double of the area. I think the average value will be doubled, okay? So here and here, all right? Okay, the average value here is more than that one because we have it frequently. So the T here is different, okay? The T here is here, all right? So you have no delta. The delta here is not exist, or the delta here, really, to be honest, the delta here is 1, okay? So if you done delta here is 1, so it will be going to this one, okay? And the same, if delta is 1 here, okay, it will be here. Why delta is 1? Because we have the signal on for 100% of the time, okay? So that's why. Okay, keep this. Please take time to understand this. I don't need actually to explain how we computed everyone, but just I want to give you more examples just to make you think about we don't need to derive the RMS for everyone each time. If there is something similar, we can really manipulate to match that to match that signal. Okay, we have another example here. That signal, okay, and that signal has the same RMS value, okay. What about this signal? Again, if we squared them and we got the same signal, so they have the same RMS value. Again, the average value for this one and for this one is 0 because it's symmetric. For the RMS value, if we squared them, it will look like this. Okay, and the same for here, okay? So I just, the squaring is approximation. I don't remember or don't actually do it the right way, but just to make it close to your thinking, okay? So the squaring is similar, so that's why the RMS will be also similar. But the average value is different because we have symmetric positive and negative portions. Again, we will be approximating some signals, example, these signals to these signals, just to make it simple for calculation. Sometimes I can't really get the ripple value, okay? So that's why I approximate it, or I assume it is 0. And once you calculate the power dissipation by this approximation here, okay, I think it's easy, no problem. The differentiation between that case and that case is very small, okay? But if the ripple is very high, so you might consider another thing, or you derive it from the beginning, and those the signals or the values that we will be using most of time. So next time I will really go through LT-Spice and show you how we use it to calculate the RMS value and average value for different signals to help us to understand really how it's computed. And also we really can apply these signals across a resistor and see the power dissipation and really validate, is it I square RMS times that resistance will be dissipating the same power as we calculate or no, okay? So see you next time, and thank you.